So next up, we're going to switch gears a little bit and go into a little bit more of a conversation mode. So I'd like to welcome John Troeltzsch to the stage. He is currently the Kepler project scientist for at Ball Aerospace. Has been at Ball Aerospace for more than 30 years, if I'm allowed to say that. Has worked on missions as diverse as the Hubble Space Telescope, Spitzer Space Telescope, and is now bringing his talent and knowledge to the proposed Sentinel mission that we heard a little bit about in Rusty's talk. So I guess to start out with, we've heard about how we find these meteorites once they've hit Earth, but how do we find near-Earth objects before that happens?
Thanks, Ryan. Well, I've been lucky enough to be building space telescopes now for 30 years, so I'm going to get back to the space telescope. But to start with, let's say you wanted to go find asteroids in your backyard. Well, you could be an amateur astronomer, you could set up a telescope, but the ones you would be finding would be ones that have already been found in catalogs. So most of the bigger, brighter asteroids that could pose a threat to the Earth have been found already. So what we're trying to do is increase that catalog that Rusty talked about, and there's a couple ways to do that. One is with a big telescope on the Earth. So if you were to build a telescope with an 8-meter mirror, and think about 8 meters, that's a big, big mirror, and put it on top of a mountain in the desert, and scan the skies in the same wavelength that our eyes see with a very sensitive telescope, you could find these asteroids and calculate their orbits. Another way of doing it would be to put a telescope in space. Now for that space telescope, it'd be a lot smaller. The diameter of the telescope would be less than a meter wide. And for that telescope, we could use the infrared. So instead of trying to look in the visible light like our eyes, we could use an infrared camera like night vision goggles to look for asteroids. And either of those approaches works well. In fact, the best approach, the most efficient way, would be if we did both searches from the ground with big telescopes as well as the space telescope and the infrared.
So when you actually find an asteroid, what does it look like in a telescope?
You know, it's funny, we've seen very few asteroids like you would see a rock in the Grand Canyon. That's because they're so far away. Really the way to see an asteroid, if you really wanted to take a picture, would be to build a spacecraft and send it all the way out to the asteroid, and NASA's got a spacecraft that's in orbit around an asteroid right now. Another way would be to wait for it to come close to the Earth, at which point you could use our big powerful radar systems to see it. But in the asteroid searches that we're talking about doing for Asteroid Day, asteroids are just points of light. You can't really see how big they are. All you can see is the point of light. Well then, how do you distinguish them from the stars in the sky? And the answer is the asteroids move against that background of stars. So if you were to take a whole series of pictures with a big telescope and then look for the things that move and then watch how they move over time, you can find the asteroids and calculate their orbits around the sun, and now you can predict whether they'll intersect the Earth's orbit, as Rusty talked about earlier.
Well, so, if you want to put a telescope into space, it's not like you just take a telescope and toss it up in the air. How do you actually build all of the infrastructure to launch a telescope into space, or what goes into the satellite required for that?
So it's kind of remarkable. Humans have been building satellites for 60 years now. That's a very short period of time. And we've come so far from very, very simple satellites to very complex. I'm the manager for the Kepler Space Telescope. But they're all fundamentally very similar. Most of them are about the size of a small bus. Some are as small as a shoebox. Some are as big as a railroad car. But they all have common elements. For example, they all have solar panels, just like the ones that I have on my roof in Colorado. That's how we generate electricity on a satellite. They all have computers. So the computer's able to take instructions from the Earth and do what we ask it, the satellite, to do. The computer also babysits the satellite to make sure that it's healthy. You know, you can't go repair it, you can't send somebody up to fix it or to monitor it, so it really has to take care of itself. Another element of satellites, you have to be able to point them very, very steady and stable, so there's special machines to do that. We have blankets and heaters to keep them warm in the cold of space. But most importantly, we build the satellites to do a job. And that job might be to take pictures of beautiful pictures like Hubble Space Telescope, of stars and galaxies or asteroids. That job might be to take pictures of the Earth like Google does, so that we could figure out how to get to Aunt Jenny's house on Thanksgiving. It might help us predict the weather. So satellites do all of those jobs to help humans achieve great things in space.
And so for the Sentinel mission, the proposal is it's actually not just in space. It's in a very interesting place in space, right? It's not orbiting Earth, but it's got an interesting perspective on Earth.
Yeah, that's right. So the satellites really go into different orbits around different objects. So a lot of our satellites are in low Earth orbit, and those are the ones that give us a lot of the weather. They go around the Earth about every 90 minutes. Some of our satellites are further away from the Earth. They're in the geostationary orbit, and they hover over a part of the Earth and give us radio communication signals or cable TV. But some of our satellites leave the Earth and go in orbit around the Sun. So Sentinel will go in orbit around the Sun, and the reason is to get away from the Earth and its glare and the disturbances and get a really good vantage point in space where we can look for these really small, cold, dark rocks without a lot of interference.
Well, in that way, it's basically going to be in kind of the orbit of Venus, so the next planet into the Sun, and sort of scanning Earth's orbit is the basic idea.
Yeah, I was watching TV last night and saw a race on a track, like an Olympic running race. And if you're on the inside lane of the track, you're going to go faster. So one of the things you can do with a space telescope is leave the Earth and go into orbit around the Sun at like Venus's distance, and then you're going to be lapping the Earth and able to look for asteroids much more efficiently.
Of course, I guess the problem is then you can't just send out a space shuttle repair crew to fix any problems with the satellite if those crop up.
Yeah, once you leave Earth, you get further and further into space. It becomes harder and harder to communicate. Think about a radio that's trying to communicate over 50 million miles. There's a lot of challenges, but systematically over the last 60 years, humanity has figured out how to solve all those problems. And today we sit in a position where we can build a space telescope to go find asteroids that might threaten the Earth.
Very good. So I think we have time for a couple of questions from the audience. So I might need someone to, so if you've got a question, you can raise your hand. Yes?
Is it totally by happenstance that most of the impact locations are just completely unpopulated?
Yeah, I think that has a function to do with how many populated areas there are on the planet compared to the whole surface of the planet. So just a coincidence, I think.
I guess kind of a lucky coincidence to think about it. But do we have any other questions in the front row?
How did you resolve the communication in terms of the distance between satellite and us?
So the question is, how do you solve the communication problem when you have these great distances in space? Well, the simple answer is you go big. So what NASA did was build some huge antennas, 70 meters wide on the Earth, and they are able to capture very, very faint signals and amplify them. So the actual satellite doesn't have a very powerful transmitter or very big antenna. The big work is done on the Earth.
All right, maybe one more question? Sure.
So the question is, how do you keep the lens clean? And it's a very, very good question. The best way is you keep it clean when you launch it, because once it's in space, space doesn't have a lot of debris. However, we have to worry about things like oil or other materials on the satellite that could deposit themselves on the lens. So we make sure that the satellite is super, super clean before we launch it, because at that point, there's nothing more you can do with it. Thank you so much.
Thank you. All right. Thanks.